At 6 meters per second, a plastic bottle travels 1 full meter in 1/6 of a second. A standard cloud inference request takes 500 milliseconds. By the time the sorting signal arrives, the object has already moved 3 meters. The ejection nozzle fires into empty air. The paper's argument is architectural, not incremental. Cloud-based AI systems, regardless of model quality or API speed, are physically incompatible with high-velocity conveyor sorting. The displacement equation does not care about the sophistication of the neural network. It cares only about the time elapsed. The solution is not faster cloud. The solution is deterministic inference at the edge, delivered in under 2 milliseconds. To understand why cloud latency cannot be engineered away, consider the life cycle of a single inference request. Encoding a high-resolution frame takes 20 to 50 milliseconds. Transmission across the public internet adds 50 to 200 milliseconds. Queuing at the data center adds 10 to 50 milliseconds. The inference itself with batch scheduling overhead adds 50 to 200 milliseconds. The return path adds 50 to 100 milliseconds more. The aggregate is 500 milliseconds, and crucially it varies. A single congestion spike at an ISP peering point adds 50 milliseconds of jitter. At 4 meters per second, that 50 millisecond variance moves the object 80 additional millimeters past the center of mass, past the nozzle, into the residue stream. The FPGA is not a faster computer. It is a different kind of machine. Where a CPU fetches instructions one by one from memory, the FPGA implements the algorithm as a physical circuit. Lookup tables, flip-flops, and DSP slices are wired together so that data flows through them like water through a pipe, without instruction fetch, without program counter, without kernel launch overhead. There is no von Neumann bottleneck. There is no operating system jitter. There is only the circuit. The key enabler is streaming vision. In a standard GPU pipeline, a camera captures a full frame, 16 milliseconds at 60 frames per second, buffers it in memory, copies it to GPU memory, and then begins inference. In the FPGA pipeline, the camera interface connects directly to the processing logic. As the first pixel arrives from the sensor, the pipeline activates immediately. The inference result for the top of the image is ready before the camera has finished transmitting the bottom. Latency drops from frame time to line time, a reduction of orders of magnitude. Quantization removes the remaining memory constraint. Converting model weights from 32-bit floating point to 8-bit integers shrinks the memory footprint by 4 times. Dropping to 4-bit integers through quantization-aware training delivers a 77% performance boost and reduces memory bandwidth by 8 times. The entire model fits inside on-chip block RAM, eliminating the external DDR4 memory bottleneck. The result is deterministic. If inference takes 1450 clock cycles, it will always take 1450 clock cycles. That guarantee is the architecture. The displacement table makes the case without ambiguity. At 3 meters per second under cloud latency, object displacement reaches 1,500 millimeters. The object has vacated the detection zone before the inference result returns. With FPGA edge inference at 2 milliseconds, displacement is 6 millimeters. Precision ejection is physically possible. The difference is not marginal, it is the difference between a working system and a non-starter. The throughput arithmetic is equally direct. Cloud-constrained facilities cap belt speeds at 2 meters per second to preserve tracking accuracy. With deterministic 2-millisecond inference, the same belt runs at 6 meters per second using SBEDIR stabilization. Throughput increases from 5 tons per hour to 15 tons per hour per meter of belt width, 300%, with no footprint expansion. For a facility running 2 16-hour shifts, that gain translates to 160 additional tons processed per day. Recycled PET prices range between $400 and $800 per ton. Cloud streaming fees and API costs for a 24/7 facility run into hundreds of thousands of dollars annually. The FPGA consumes 10 to 20 watts. A comparable GPU setup consumes 100 to 200 watts. The consulting industry has a name for what most AI vendors sell in this space. Application layer integration, layer 7. They wrap a cloud API, deploy a dashboard, and call it machine vision. When the network drops or an ISP peering point spikes, the sorting line stops. The system reverts to safety mode, zero sorting. Veriprajna operates at layer 1 and layer 2. The vision pipeline, the quantized neural network. The valve synchronization logic, all of it runs as hardware on silicon, isolated from the Linux partition handling reporting. Even if the cloud connection fails, the FPGA continues to sort at full speed. Any developer can identify a bottle in a static image. Few can identify and eject that bottle at 6 meters per second in a chaotic waste stream with 99% purity around the clock. We built this architecture to operate where cloud cannot follow. Read the 18-page brief, approximately 25 minutes, to walk the full displacement model, the AMP SoC architecture, and the quantization pipeline.